I want to call your attention to the graph here. This is a graph of a moving vehicle. The x-axis represents time in hours, and the y-axis represents distance traveled in miles. The question is, what is the velocity of the vehicle? And I encourage you to pause the video for a moment and think about how you would calculate the velocity of the vehicle using this graph. Hopefully, you looked at this and thought of a way to do this. Hopefully you remembered that velocity can be calculated as the change in distance over the change in time. Hopefully also that you are familiar with this little delta symbol, which means change in. It used to represent change in. So we have a rate of change here. We have how much distance is changed in a certain amount of time. So we could pick any 2 points on this graph. So from at 1 hour, we're at the distance 40 miles, traveled 40 miles. At 3 hours, we've traveled 70 miles. And at 5 hours, we've traveled 100 miles. We started out at about 25 here. So this would be 0, 25. So we could take the distance, the change in distance between any 2 points and figure this out. So for example, we could look at the change in distance between 140 and 370. We could say there's a difference of 30 miles over a difference of 2 hours, 3 minus 1. So we'd have 30 miles in 2 hours, or 15 miles per hour. We could do that with any other points. I could do that with the 5 and the 100 and the 0 and the 25. And I could say our change in distance over change in time is a total of 75 miles in 5 hours, which would end up being 15 miles per hour. Okay, so there's numerous ways to figure that out. Now, what quantity on the graph am I actually measuring when I do this? Hopefully you recognize, I'm saying hopefully a lot, haven't I, in this video? Hopefully you recognize that the change in distance over the change in time is the change in y over the change in x, and the change in y over the change in x equals slope. So the slope equals the velocity in this problem. And if I further asked you, what does the fact that this is a line tell you about that slope and that velocity, you would recognize that the velocity is constant because we have a linear graph. Okay? Now the question is that realistic? How realistic is it for a vehicle to be going 15 miles an hour at a constant rate for 5 hours? Now, maybe if you were driving through North Dakota on a completely deserted highway, you might be able to put your car on cruise control and drive exactly the same speed for 5 hours. That might be possible, but that's probably not realistic for most situations. Cars and vehicles stop, start, change direction, go up hills and down hills. So in real life, a variable slope, a variable rate of change of distance over time is much more realistic. So well, how do we deal with that? We're going to look at this bird in flight, and we're just going to say, for the sake of argument, that this graph represents the flight of a bird. Right now the bird is sitting on a tree branch 3 meters above the ground at 0 seconds, and then it spots a delicious bug that it wants to eat. So it flaps off the branch, dives down, grabs the bug, and then swoops up and swallows it. Okay, so if I asked you the question, what is the velocity of the bird, you would have to qualify your answer because, well, the velocity of the bird when it starts out is a positive. It's going up, you know, not very fast maybe, and then it kind of swoops down pretty quickly in a negative, sort of a fast negative velocity, and then it swoops up in a positive, even steeper or faster velocity. So it's not a constant velocity. So we have a problem here. Velocity is not constant. I can't just find the slope of a graph and it's the same all over. For example, if I wanted to know the velocity in the interval of time from 0 seconds to 2 seconds, even then it changes. You can see that velocity this is a curved graph, but maybe we could find the average velocity. The average velocity would be the change in x. Okay, so if looking at these 2 points right here, the change in y would be 1 minus 3 from the 2 seconds to the back to the 0 seconds. The change in y would be 2 minus 0, and we would end up with negative 2 over 2, or negative 1 meters per second. Now, if I'm looking from 2 seconds to 3 seconds, so then I'd be looking at the 2-1 and the 3-6, I could say the average velocity is equal to 6 minus 1 over 3 minus 2, which would be 5 meters per second. So in one place it's going negative 1 meters per second, another place it's going 5 meters per second, or maybe I could look at the overall average from 0 to 3 seconds and say the average velocity is equal to 6 minus 3, that's the change in distance, over 3 minus 0, that would be 3 over 3, or 1 meter per second. But no matter what I do, these average velocities are, every 2 points I pick, I'm going to get a different average velocity. And what if I wanted to know the velocity at a particular point? Could I find the velocity at one particular instant in time? That would be very useful. How do I do it though? So let's say I want to find the velocity at 2 seconds. That would be where x equals 2 and y equals 1. So that would be this point right here. I'll mark it in red. I want to find the velocity right there. That would be difficult because to find the average velocity or the slope, I need 2 points. So I've got a problem. I only have 1 point. How do I do this? Well, I want to remind you of I'm trying to find an extra, go to another page here, but I can't get to my little thing. Just a second. I want to remind you of a couple definitions. If I want to find a tangent line to a point, remember on a circle, the tangent line is the point that just touched one single point on the circle. That's actually not a terribly great tangent line. There we go, that's a little better. And it doesn't cut into the curve any place else. Whereas a secant line, so this is my tangent line, whereas a secant line would cut through 2 points and the curve kind of sticks out on this side. So this is a secant line. And we're going to look at how a tangent line and a secant line can help us in this situation. So for the bird in flight problem, let's take a look at a tangent line. So here's the graph. I'm going to zoom in just a little bit here. And look at the tangent line. So notice right here, when the bird is ready to take off, it's going to take off with a positive velocity. That slope is positive there. When we get to, as it changes direction, the slope kind of momentarily becomes 0. And then we have a negative slope. Notice it's getting faster and faster, steeper and steeper. Now it's starting to get a little less steep until we get down to the bottom here. We have another 0 slope. I can't get it exactly right there at the 0, but you can see that the slope pretty much levels off to 0, and then it moves up and becomes a positive slope, getting steeper and steeper and steeper. Okay, so, but I'm particularly looking for the slope at the point 2, 1. So if I know the slope of the tangent line at 2, 1, I can, that's the same as the slope of the graph, it turns out. And you can see that this looks like a slope of about 1. Looks like we have about 1 over 1. It's hard to show exactly where the tangent line is, but that looks pretty close. So I can estimate by drawing a tangent line. So estimate slope using the tangent line. I need to write this somewhere else where it will fit. Estimate slope using a tangent line. Okay, so here would be my rise over run, and it looks like it's approximately 1. So let's define a couple terms, and then we'll look at how to find exactly what the slope of the tangent line is at the point 2, 1, and the slope of the graph. So the derivative is the slope of the function f of x at a particular point on the graph of f of x. We can also say that the derivative is the instantaneous rate of change. Slope is rate of change. Instantaneous range means rate of change at a particular instant. So it's the instantaneous rate of change of f of x at x equals at a certain x value on the graph. We can also say that the derivative is the slope of the line tangent to f of x at a particular x value. In the next video then we're going to look at how do we actually find the rate of change, that instantaneous rate of change, that slope of the tangent line, that derivative at the point 2, 1.